Have you ever wondered, what if the things we build could just build themselves? No, I'm not talking about robots or giant factories. I mean on their own, just by adding a little bit of heat. Well, today, we're going to look at a totally new kind of origami that does exactly that.
Okay, so check this out. On the left, you've got this completely flat, laser-cut pattern. And then, poof, on the right, that exact same piece of material has folded itself into a perfect cube. There are no hands, no motors, no hidden wires. So the big question is, how on earth is that even possible?
Well, believe it or not, this isn't just some cool party trick. According to the research paper we're diving into, this could be a solution to a really fundamental problem in how we make, well, pretty much everything.
Just think about it for a second. The way we engineer things, whether it's that piece of flat-pack furniture you dread building or a multi-million-dollar satellite, it's always complex, it's expensive, and it takes a ton of time to assemble. But then you look at nature, and nature's just the absolute master of self-construction. From a leaf unfolding in the sun to proteins folding into tiny biological machines, it's all fast, it's lightweight, and it's completely automatic.
And this is the really powerful idea, captured perfectly right here by the researchers. Self-folding could automate the whole construction process, from things too small to see all the way up to human-scale structures. The potential here is just enormous.
So how do they actually pull it off? Let's peel back the layers on this self-folding magic trick and see what's really going on inside.
The secret, of course, isn't magic. It's just some seriously clever material science. What you're looking at is basically a 3-layer sandwich. You've got your structural layers on the top and bottom. In this case, it's just plain old paper. And then there's something really special tucked away in the middle.
That special something is a shape memory polymer, or SMP. This stuff is a type of smart plastic that you can program to remember a shape. You can stretch it out, flatten it, change its form, but as soon as you apply a trigger, in this case heat, it wants to shrink right back to its original memorized size.
Now, here's my favorite part, the big reveal. This advanced, heat-activated smart polymer at the very heart of this technology is basically the same stuff as the kids' craft toy, Shrinky Dinks. Yep, that's right. It's an inexpensive, easy-to-get sheet of pre-strained polystyrene that is absolutely ingenious.
And get this, making these self-folding sheets is surprisingly simple and super fast. You just laser cut the patterns into the paper and polymer layers, use a special high-temperature silicone tape to bond them all together, and then one last cut with the laser releases the whole device. It's that easy.
And here you can see what that process looks like in the real world. You see the separate, precisely cut layers being lined up and then laminated to create that final composite sheet. The key takeaway here is that the whole method is designed for really rapid fabrication, using tools that are relatively inexpensive.
So how does a flat sheet actually bend? Well, it's all in the design of the hinge. When you heat the entire sandwich, that polymer layer in the middle tries to shrink. But notice the clever trick. There's a gap cut into the top layer of paper, but the bottom layer is left solid. So as that middle layer shrinks, it pulls the two sides of the gap together, forcing the whole sheet to fold upwards.
And here is the most crucial part of the whole thing. The engineers can precisely program the final angle of the fold just by changing how wide they make that gap. A wider gap creates a sharper, tighter fold. And as you can see from the graph, their computer model almost perfectly matched the real-world results. This gives them incredible control over the final 3D shape, all encoded in a simple 2D design.
The theory is just beautiful. It's so elegant. But does it actually work when you start trying to make more complex shapes? All right, let's see how this technology performs when it's really put to the test.
Here's our cube again, but this time we see it in action. At time 0, it's flat and gets placed in an oven. After just 18 seconds, the folds start to activate. By 20 seconds, it's already taking shape. And in less than a minute, you have a fully formed, rigid cube.
But it's not just for simple little boxes. This is an icosahedron. That's a super complex 20-sided shape. On the left is the flat pattern, and on the right is the incredible 3-dimensional structure it folds itself into completely automatically.
And the technique isn't limited to just straight lines either. It can also create these much more organic, elegant shapes with curved folds. I mean, this beautiful flower pattern really shows off just how versatile this method is.
Now, this might just look like another cool, complicated pattern, but it's actually the world-famous Mura fold. This is a big deal in engineering. It's used for things like deploying huge solar panel arrays in space. And right here, we're seeing a large sheet of it assemble itself from flat to folded completely on its own.
Now,
Through all these experiments, the researchers learned something really important. For shapes like the icosahedron, where the folds happen one after another in a sequence, little errors in one fold can add up and affect the final shape. But for patterns like the Miura fold, where tons of folds are working together at the same time, the errors actually tend to cancel each other out. And that makes the whole process much more reliable and repeatable.
A self-folding shape is great, but for a lot of real-world applications, it also needs to be strong and permanent. And that led to the next big innovation, making these structures seal themselves shut.
And the solution was wonderfully simple. Hot glue. By applying a hot melt adhesive along the edges of the flat pattern, an adhesive that's designed to melt at the exact same temperature, the structure literally glues itself shut as it folds, locking its final shape into place for good. So, did it work? Oh yeah, it worked. This chart shows the results of their compression tests. The self-sealed structures were able to handle nearly twice the load compared to the unsealed ones. This simple little addition makes the final product significantly stronger and way more durable.
So you take this simple, rapid, and inexpensive technique, inspired by ancient origami and powered by a children's toy, and it opens up a completely new way of thinking about how we manufacture things. And it leaves us with one final, kind of mind-blowing thought. What if the next satellite, the next emergency shelter, or even the next complex robot could be shipped completely flat, and then, with just a little bit of heat, just build itself?